Hello, everybody. My name is Daniel Holmlund. I am a software developer at Intel with their Intel IoT Developer Program. My job is to set technical direction for our hackathons and workshops within the IoT group. And today we're going to be talking about two things that are very interesting from the point of view of automation and IoT. That is the up-and-coming prevalence of voice assistants and how we can integrate that together with IoT automation. So we're going to go through a couple of different scenarios, and here's what I want you to think about as we're doing this. So first of all, we're going to do an overview of the cloud and edge components that are needed to enable voice IoT automation. There are several popular agents that are out there currently, including Amazon Alexa, the Google Assistant, and Mycroft AI. We're going to install all three of these on a single Intel IoT Gateway and show you how to enable each of these voice assistants on those gateways. Next, we're going to look into what they do in terms of taking voice and moving that up into the cloud, or in the case of Mycroft AI, rendering it locally, into an API that's actionable. And most of the systems call this rendering it into an intent. So we'll go over the cloud components that do voice to intent conversions. These are Alexa Voice Service, Google Actions, and Mycroft Intent or Mycroft Adapt. The next area that we're going to look at is intent fulfillment. So once you've actually taken the voice and converted it into an actionable type of API or intent, how do you go about satisfying that intent? So to give you a really quick example, if I ask my smart assistant to order me Domino's pizza, that voice is going to go up to the cloud. It's going to be converted into an intent to purchase from the Domino's pizza store. And then that intent is going to be forwarded to a fulfillment service, probably hosted by Domino's or on one of the cloud solutions. Or, of course, you can host it locally as well. And I'll go through and show you how to write your own microservice in order to do intent fulfillment locally within your own edge network on an Intel IoT Gateway. And next, we're going to build an automation service that, whether you've taken the path of fulfilling that intent through the cloud or you're doing it all locally on your internal network, we're going to show you how you can build an automation service that will take APIs and, using libraries such as libraw and libupm, convert those into actions that can intelligently change IoT devices on your network. So for instance, you can turn the lights on, turn the lights off, turn the coffee pot on, do those sorts of actions. We'll talk a little bit about how state is communicated all the way through these workflows. So let me start off right here with the state at the Intel IoT Gateway. We're going to assume that we're starting with an Intel IoT Gateway and a variety of different things over here. You see I have a house and a couple of gears and a factory icon. These things are representative of the devices that are on your network. The Intel IoT Gateway is also on your edge network. The edge network is your private network. And of course, the cloud is any third-party or outsourced services that you're using within your workflow. So the first step is to look at the Google Assistant, Amazon Alexa, and Mycroft and install them onto the gateway. In order to do this, you have to configure projects within the cloud, at least for Google Actions and for Amazon Alexa. You'll have to create a project for each of these. You will need to set up OAuth authentication tokens, a client secret. You'll have to share those with the gateway so that it'll know how to communicate to these services that are in the cloud. In the case of Amazon, you also need to set up your IAM security permissions. And all interactions are, of course, encrypted going between the cloud and the edge network. Next, we'll show you, once these services have rendered the voice data into an API, how you can send that back down to the Intel IoT Gateway. This service is actually running on the Intel IoT Gateway. Or if you want to, you can forward it onto a cloud. So this is a scenario that Intel often talks about, and that is, what is the advantage of having compute power at the edge? When we talk about a gateway, just to put this into perspective, a gateway is simply a computer which manages a variety of different IoT devices on your local area network. It might It might speak in multiple protocols. For instance, it might have LoRa ability, Zigbee ability, Bluetooth ability, Wi-Fi ability, Z-Wave ability. There's a variety of standards that are out there. But it communicates over these protocols to the local devices that are on your network and relays that information up to cloud and local services that are able to use them. Now, there are gateways that we use every day today. The Amazon Echo device is a gateway that simply takes sound information and conveys it up to the Alexa voice services. The Google Home is a voice to API gateway. If you've purchased a Philips Hue light bulb, you know that it comes with a Wi-Fi to Zigbee gateway. And you know, to be a little more fun with this, when you, if you're a fan of Star Trek, as I am, you'll notice that when somebody is talking to the computer, for instance, if Captain Picard is talking to the computer, he doesn't go over to the warp nacelle and ask the thing itself to respond. He's going to respond to this disembodied voice that's in the air. The computer in this case is a gateway that will talk to the replicator or whatever device they happen to be communicating on. So it's advantageous in order to have extra compute power on your gateway when you're doing these types of voice activities, because not only can you install a voice agent here, but you can install extra services that you wouldn't normally be able to do on other devices. For instance, we'll write our own voice fulfillment service and install it on the gateway here as well. We'll write our own automation service that's capable of taking the fulfillment message and assigning a function or an action to it. So we're going to walk through this workflow, both in the cloud, coming through, and finding the entry points down to our local edge network. So if we want to move this workflow to our local area network for privacy concerns or cost concerns, or simply because it's corporate policy to do so, we'll show you how to do that. So a couple of questions to consider. Do I want to enable every IoT device with a voice assistant or just a gateway? How do I represent the state of an IoT device? So as you are speaking to a gateway, that gateway needs to be able to render your voice into an actionable machine data structure that can be passed along the workflow in order to enable your action to occur. How do you represent state of a device within your workflow? How do I build a voice to IoT automation workflow? That's the main point of this entire talk. And how do I build the same type of workflow on the local area network? What are the trade-offs in building in the cloud versus the edge? One really quick trade-off might be that in the cloud, you have a variety of artificial intelligence teams that are working in order to improve the experience of your voice to text and natural language processing conversions. If you install everything locally, then you are doing that training either locally or participating with communities in a fashion in order to bring models onto your local system, and all the processing is done locally. The advantage to that is, of course, privacy, secrecy. If you want your data to remain on your local area network only, this is a good way of doing it. All right. First of all, installing voice assistants on the Intel IoT Gateway. I'm going to show you a video here of the end of this section and what we were trying to accomplish. So let me start the video here.
Hello everyone, this is Daniel Holmlund coming to you from one of the Intel labs. I just wanted to give you a sneak preview of my talk at the Global IoT DevFest this next Friday and Saturday. So what I have right here is a couple of Intel gateways that are connected up to this microphone here. And we have a couple of different virtual agents that are installed. Let me show you. For instance, if I click here, Alexa, what time is it?
The time is 1:02 p.m.
And down here, Google, what time is it?
The time is 1:02 p.m.
And up here in this area, hey, Mycroft, what time is it?
3:02 p.m.
So here you can see that I have Alexa, the Google Assistant, and Mycroft AI all set up on the same box. And I'm looking forward to showing you how to do home automation as well as cloud-based automation at the Global IoT DevFest.
So that was a little demo of what we're going to try to accomplish here. Now, I'm not going to go through all the steps in order to do this. I'm going to take you through the high-level points because, quite frankly, at this point, between the three services, I have to say that Mycroft was the easiest to install. Amazon and Google are both very much an evolving set of projects, as Mycroft is too. But at the moment, the best way that I've found to go about installing Alexa is to use one of their sample applications, and that you can find at developer.amazon.com. So if you go to developer.amazon.com and click on Alexa, you'll be presented with these two windows. The first one here, the second one here, is the Alexa voice service. This is what you'd click on in order to install the Alexa voice agent on a local device. So we're going to click on this here. The first one over here, first option, is Alexa skill building. A skill is the ability to teach Alexa to respond to new and different voice commands or questions, and to go about writing a fulfillment service that will fetch the data that you need in order to answer the question and return that information to you in a voice format. So once you click on this second option here, voice service, you'll be asked a standard battery of questions, such as what is your device ID? Can you choose a name for it? And most importantly, over here in the security profile, you'll be asked to set up your security role, which is an IAM role within Amazon. And you'll receive a security profile ID that's associated with a OAuth 2 client ID and an OAuth 2 client secret. These secrets need to be taken down to the gateway itself for the local side of the setup. So this is the cloud-based portion of the setup. The local setup is fairly involved. There's three different agents or three different parts that you need to set up in order to create an Alexa-enabled device. And again here, we're going to be using the the Alexa voice services. The Alexa voice services are a set of APIs that allow you to communicate to their back end and do voice processing. However, in our particular case, we've taken a sample application they've provided for us that's written on top of these voice services. That sample application is right here. You can go to Git clone, GitHub, Alexa AVS sample app. And there's a couple of different components of this app. The first part is there is a Java client. This particular project is written in Java. The Java client, it uses the VLC audio APIs in order to record your voice and set up an OAuth session and to send that voice data up to the Amazon voice services, the Alexa voice services. You need to run a script in order to create your self-signed certificates and communicate those certificates back up to the cloud in order to set up your encrypted connection to the cloud. The second portion, so the first part is that Java client app, which records your data, sends it up to the cloud. The second portion is the part that receives data back from the cloud and reacts to it, either by speaking or usually in this case by speaking. But if we go through a fulfillment cycle and create a webhook for fulfillment, we can send that data on to our automation service, which we'll talk about in a moment. So this portion is called the Node.js companion application, and it simply listens for the response from AVS and then creates a voice output. The third portion that I talked about is the wake component. Now, this is an optional component. There are a variety of different user scenarios where you can wake up your Alexa device through a keyword or by saying, well, I won't say it here because you probably have some in your room. But let's just say I set mine to computer, and whenever I watch Star Trek, it goes off continuously. You can set it up through a wake word, you can set it up via tap, or you can set it up via other types of events. For instance, you can connect a button to an IoT device and have it set up a wake command. For the Google Assistant, this was a fairly involved process as well, and whether it might be encouraging or it might be a little frustrating, but it's a very actively evolving process. I noticed several times that over the last 2 weeks while I prepared for this talk, the Google documentation around the voice assistant changed. I believe I noticed seven times that it changed. So the team there is actively updating the documentation, and it's becoming a very large set of documentation to lead you through the process of doing this setup. But the basic idea is that you need to go to the Google development, go create a Google developer project. In that project, you need to enable the Assistant API. You need to enable billing on that API, and of course, set a budget. And then you need to be able to create your OAuth client ID and token and download that in JSON format. And just to give you a clue what that looks like here, I'll show you. I got it open. Actually, I'll get back to you there. I'll have to go hunt for that particular one. The client is built on Python 3. So first of all, we install a Python 3 environment, and in Python there is such a thing as virtual environments, which basically creates the directory structure needed in order to run applications within a directory space, and changes the environmental variables, etc., to be self-contained within that space. So we set up the Python 3 environment, and we call pip, the install manager, in order to install the Google Assistant library and the Google OAuth library. And we hand our secret token over to the Google OAuth library and launch the Google Assistant demo. The first thing it's going to do is it's going to pop up a dialog box or a command line and ask you to go to a URL. It'll bring up your Google logon screen and ask you to allow this particular application to talk to your account. And then it will hand you a token back, and you can paste that token back into the terminal. And after that, the terminal will wake up whenever you press the enter key. The second option that we have down here is through Google remote procedure calls. If you don't want to use Python right now there aren't as many sample applications in other languages. So Python is the main way that I saw that made it easy to install the Google Assistant. But it's all based on these Google or G remote procedure calls. This is a lower level API that will allow you to generate interfaces in any language that you choose. So C#, C, JavaScript, Python, whatever you choose. And you can build your own client library on top of that using gRPC. All right. So both Google and Amazon require cloud and local components. We've already gone over that. We've talked about how OAuth needs to be set up for secure communications, how the wake word is set up here. And in the case of these agents, we are using the keyboard and mouse in order to do the wake for our agent. Mycroft, however, does not require a cloud component. And this is its primary advantage, in addition to being fully open source, which is excellent in and of itself, community-driven and community-contributed. It doesn't require that you go to the cloud. All voice processing is done locally, and all voice-to-intent mapping is also done locally. What I would stress about this, however, is that it does not mean that you can forego encrypting in between your various different services that you deploy on your local edge network. You should always have encryption and good security practices in place for when you're moving data around the network. Amazon uses HTTPS version 2 in order to communicate the audio data. So it's either done in chunked format or in a single upload if the audio file is small enough. The audio is encoded in MP3 format. Google uses the gRPC bindings that we talked about earlier, which gives it direct access to the voice request. Let's see. So once the voice data is moved up here to Alexa and to Google Actions, there is a process that is gone through in order to break these voice commands down into intents. So the first thing that the developer needs to do when they're trying to create a new process or a new skill or a new action is that they need to list a number of example phrases of what a person might say in order to invoke their intent. So a sample phrase might be, please turn the lights on, or are the lights on in the family room? Please turn the brightness of the lights up to 50. Please set the lights to pink. And these examples will be matched to an intent here on the back end. Once this matching is done, and you do need to give several examples of each phrase. All three of these services will then use deep learning and neural networks and statistical calculations in order to match the example text that you've given it to a particular intent. So this is somewhat of the secret sauce that Google and Amazon have in their cloud services, their method of matching voice data to intent and doing their natural language processing as well. That's also one of their main advantages, is that they're continually learning and growing. What is an intent? So an example of an intent, you may want to get some more text from the user. So if text goes to the clouds, for instance, if you say, Mycroft, well, not Mycroft. If you say, Google, please set a timer, that text will be sent up to the cloud, and an intent will be rendered to ask the user for a time period that it needs to be set to. That time period is an intent which is sent back down to the voice agent. The voice agent will then ask a question, how long would you like to set the timer for? And that information is relayed up to Google Actions. So here is an example of once the phrases are matched to intents, each intent has a series of entities that are associated with it. This will probably become a little more clear as I do a demo. But entities are keywords within the phrases that can be converted into parameters and used within an API call. So for instance, one of the key phrases here, or two of the key phrases here, is the word on and lights. On in this case relates to a state. Lights relates to a device. In the phrase, are the lights on in the family room, we have a device and we have another key phrase which relates to a room. So by identifying these key phrases and adding them into a JSON data structure, that JSON data structure can be passed along to the fulfillment service in order to find the right data and to perform the correct actions that are needed by the end user. Okay. The Mycroft Adapt Intent Parser. This is an open source software library for converting natural language into machine readable structures. I am just going to play the video here, and hopefully this will give you a good overview of what a parser does that converts natural language into intent.
The Adapt Intent Parser from Mycroft AI. The Adapt Intent Parser is an open source software library for converting natural language into machine-readable data structures. So put simply, Adapt helps computers understand the way people talk in everyday life. To demonstrate this, a user might say, play the Daft Punk Pandora station. The Adapt engine takes this input and translates it into a JSON data structure that can be read by the application. The application can then take that information and turn it into an action. In this case, it will play the Daft Punk Pandora station. Adapt was developed at Mycroft to quickly and accurately determine user intent from voice commands. Over its life, it will continue to receive updates from the Mycroft team and community. The Adapt Intent Parser is now available with an open source license and can be used for a variety of projects where people interact with natural language such as chatbots, robots, video games, phone systems, analysis of large amounts of data, and many more exciting possibilities. We're excited to see how you might use this innovative new tool. You can find the resources you need to use and contribute to the Adapt project at mycroft.ai/adapt. You can also engage in the community around the project at community.mycroft.ai. The source code is available on GitHub at github.com/mycroftai.
So I see one question, what languages are available? It depends on which of these services that you're using. For Amazon, Amazon has Node.js, Python, Java support. And I'm sure that if you want to go down to lower levels, you can support your own languages as well. The same is true with Google. Google uses Java, Python, Node.js, as well as if you want to generate your own gRPC bindings, you can create your own libraries. Mycroft, I'm sure, has a variety of language bindings. However, the one that I saw the most of was Python. So there's a large, most of the skills that I have seen online are written in Python. But I'm looking forward to playing around with all three of these more and finding out more about them. So I wanted to show you really quickly some of the tooling that Google has, as well as Amazon, for creating these intents. In this particular case, we have the intent here along the top. We're going to check our the brightness of our smart lights. We can enter in a variety of different phrases for these, and they map to different actions that are created here. Let me show you the same thing over in, or not the same thing, but let me show you how Amazon does this as well. So if I go over here to my interaction to Alexa skill sets and do Alexa skill building, you can see that I've built a really small session here that has the 3 basic intents that are required by an Amazon skill: the cancel intent, so if you say cancel, the help intent, so the user can get help, and the stop intent, which also exits the particular skill or device that you're using. So here I've created a new intent called Smart Home Device On and Off, and I've entered in a few phrases that might be invoked here. So you might say, turn on the device to a certain state. And if I define devices down here, I can click on these. Devices are defined as thermostat, outlet, and lights. These are what Amazon terms as slots. Mycroft and Google term these as entities. The state can either be on or off. So as we go up here, we can say other things. We can say outlet should be on, and then tag these as this is the device and this is the state. And we can see in our code editor up here that a series, a JSON object is being built up that has the different intents that we have here, samples that are associated with each of these intents, the devices and the states, and what those devices and states, what the parameters they can take on are, and whether they can be on and off. So once this is done, you can go over and test the putting together of these JSON structures and forward them to either the cloud services that you're going to be using or to your own service. Let's go look at that now. So we've talked about how Google Actions will take your voice, convert it into a JSON structure, the same with Alexa voice services and the Mycroft DAPT intent parser. Next, we can choose to either forward that information back down to the gateway where we can do our in-house, or we could forward them on to further cloud services. In the case of Google, they have a service called Google Cloud Functions. This is part of the serverless movement. The idea here is that for both Amazon Lambda and Google Cloud Functions, you write function code, and you don't need to worry about how to scale it or what processor it's being run on or what operating system it's being run on or any of the system administrative tasks that normally you do have to be concerned with if you're running your own server. In this case, we just have code. It's executed and automatically scaled for you. All right. I want to give a shout out to this particular framework called Serverless. If you want to see how to start writing endpoints for these different services that provide serverless functions, this is a great place to start. I highly recommend you go here. You can also run these locally on your local Intel IoT Gateway. So this is a good way to get started with writing functions that you can move seamlessly in between your local edge environment and the cloud environment. I also want to give a quick call out to their documentation. Wonderfully organized documentation, and it's I highly recommend you go through it. For Amazon Alexa, once you create a Lambda function, there are a variety of different templates that you can use. So in this particular case, we are using Node.js and filtering by Node.js. On Google, Google will give you a variety of starting templates as well. Here is one of their starting templates, the Hello World template. In this particular case, I'm using the API AI Assistant library, which is a library that allows you to respond to your assistant instead of responding with HTTP codes and sending raw JSON files. You have helper functions that allow you to send text and ask questions and create dialogues. So in this particular case, we're setting up a map of actions. These actions correspond to different intents that are sent from the Google Actions Cloud service. And these intents can be fulfilled in your response handler. Let me show you the service. Actually, before I go to our microservice that I wrote on the Intel IoT Gateway in order to receive actions from the cloud and turn them into an action we can process locally on our edge network, I want to show you how to configure the endpoints so that instead of going to the cloud, we head down to the Intel IoT Gateway. So let me do that first of all by going over to API AI. So in API AI, if you have an account here and you have built up some type of agent, for instance, I built up an agent here to help my daughter with her addition, subtraction, multiplication, and division tables. So she can go over to the Google Home and say, hey, I want to play the adding game. In that particular case, we need to come up with a back-end service that will create a problem for her to solve, like what is 4 plus 5? So in this particular case, what I've done is I have turned on webhooks. And yes, that is my webhook. No, it is no longer active. Or yes, it is no longer active. But this webhook is a VPN tunnel which will allow my Intel IoT Gateway to have a publicly accessible IP address. So I can open up this endpoint here that allows Google Actions or Alexa voice services to call a webhook and send a JSON object down to my local environment, my voice fulfillment service. And then my voice fulfillment service is going to create an action that the automation service will handle. Back over to, and then I wanted to show you this as well in Amazon. In order to configure Amazon, I guess I will save my voice model. Okay, my voice model is saved. If I want to go over and choose between going to the cloud or going to the edge network on Amazon, I can go over to configure here. And you see I have the option of sending my skill JSON object to an AWS Lambda ARN. So I can set up a function here to forward my JSON structure to, or I can forward it to an HTTPS endpoint. And again, in that case, my HTTPS endpoint is simply the VPN tunnel that I've set up in order to expose a public IP address to the Intel IoT Gateway here. So on that, I have a microservice running, not this one, that simply is labeled as the, in this particular case, I'm going to turn on a light bulb. So it's called Light Bulb Fulfillment Endpoint. And on my local area network, on my Intel IoT Gateway, I have a Mosquito server running that's using encrypted MQTT. So it's MQTT over TLS. I didn't set up the encryption in this example here because it would have caused the example to scroll off the top of the screen. So I reduced it down a little bit just to show the essentials of how to set up an MQTT connection, connect to the client, send off a request where the light bulb's value is set to on, and publish that, and then return an OK to the cloud service that sent the request. So one thing to note here is that once a request has been received, I've created this structure that will contain the state of a particular light bulb service. Now this is going to be forwarded over MQTT on the sensor's light bulb data topic, and that is going to be received by the automation service. So let's see how the automation service does that as well. So that MQTT request is generated here after HTTP has sent a JSON object over representing the state change to occur. And then this service, the automation service, which is on the edge network, it could be running on your Intel IoT Gateway, or it might be running on a separate service. One of the advantages of having extra compute power on your gateway is that you can run the database, the Mosquito service, the voice fulfillment service, the automation service, all of these things on a single computer that is responsible for managing and looking after devices on your network. So I'm going to go through a fair amount of code here, but let's do the setup for the automation server. And it looks like I have 4 minutes to do it in. So we're going to make this quick. The automation server is responsible for sensor and data commands that are communicated over MQTT TLS. It's communicating via a Mosquito broker that is running on the Intel IoT Gateway. The automation rules are stored on a MongoDB database that I have running on the Intel IoT Gateway. And local fulfillment functions, such as the one that I just showed you, are responsible for admitting a JSON object that contains the state of the IoT device. In Amazon services, for instance, this state right here might be called a shadow device. It's basically a data structure which represents the functional state of a device. Another thing that I did to make it easier is I wrote a simple user interface to show me how many sensors are on the local area network and how many business rules I have, how many actuators I have, and how many errors are currently here. If you're interested in getting this, you can look for it at the Intel IoT Developer Relations GitHub repository here. So we have lots of, here's the automation service that I'm going to be going through. If you want to see the code for the automation service, it is here as well. So rather than going through slides about the code, I'm just going to show you the code itself. First of all, actually, before I do that, I want to talk about what is a trigger. So a trigger is a business rule that has a function that returns true or false, a predicate function, and a function that invokes an action. So in the case of the JSON structure that we just created, we said that the light bulb's value is equal to on. This function here is going to be looking at all the MQTT traffic on our network and comparing the value of the sensor to its state. And if this is equal to on, then it's going to invoke the function that's below. So in this particular function, I have an HTTP request. This might be familiar to people who have developed with the Philips Hue lights, but the HTTP request to the Philips Hue bridge, giving it an ID of a light bulb and a state to set it to. And then I simply print out to the log file or to the console, the color has changed or it hasn't. So here is the software for this. I'm going to quickly go through this. First of all, we're setting up our MQTT libraries, our connections to our MongoDB database, and we're loading up Lodash to be able to perform some utility requests on JSON objects and the promised request library. We use our key, our cert, and our trusted certificate authority in order to set up an encrypted MQTT over TLS session. We add our MQTT over TLS session variables here and connect to our client. Whenever we receive a connect command, we're going to print to the console, connected to the MQTT server, and subscribe to all the sensor data. One thing that I should note here is that this particular automation server is part of a lab series that we run called the Commercial Internet of Things Workshop. And this is a lab that's designed to be designed and implemented by students in less than 1 hour. So there are a lot of potential additions you can make to this, but this is probably about the simplest you can get in order to create your automation service. So the automation service is going to connect to a database at a given database URL. Print connection successful when it connects. And then I'm loading up 2 models. I'm loading up the business rules or automation triggers and the context object here. This is an object which is going to be passed into the trigger itself. If I want to be able to access MQTT or HTTP within the automation rule, I need to load the library here and pass that into the trigger. Here I retrieve the database rules from the database and instantiate each one of them. And I'm listening to messages here with our MQTT client. As messages come in, I parse the JSON for it. I determine if this is a sensor topic or an actuator topic. And if it is, I'm just going to skip down here. If it is, we're going to find the sensor that's associated with it and pass in a list of all the triggers that are associated with that piece of data. So for instance, if we have a light bulb and its value is on, we're going to load up all the triggers that are related to light bulbs, and we're going to go through them to check to see if their predicate function evaluates to true. If it does evaluate to true right here, then we're going to execute the trigger function. And this is the basic way in which you can automate services on your local area network. If I go over here to the service that I set up for editing these, you can see that I set up a couple of different rules here. Temperature is greater than 27, temperature is less than 20, or voice activated light rule. And these will execute on the Intel IoT Gateway. And you can write your libmra and libupm functions in order to turn your light bulbs or call the APIs to turn your devices on and off. Is the lab on GitHub? It is, Johnny Chan. So again, go over to this area here. You'll find all the different labs, as well as information on the workshop that I mentioned earlier. This can be done on a Raspberry Pi as well. However, an Intel IoT Gateway will give you a lot more horsepower, so you can run more automation services, talk to more sensors. You can scale it up in a large fashion. Okay, so I'm out of time, but I'll take questions for the next 5 minutes. Otherwise, I'll let you go to your next session. Thank you very much. Question is, can you use an Intel Edison for these? Yes, you can use an Intel Edison. So Intel's strategy in this area is to use a variety of different sized processors to fit different types of needs. If you are just looking at home automation, something like an Intel Edison, thank you, Johnny Chan. Forking repos is an awesome thing because I love working with other people and I love seeing community work on these types of projects. One thing you should keep in mind is that these projects are not engineered to be an end-all be-all. They're engineered to be lab sessions that students can accomplish within a 1-hour time period. I'm thinking about making a more professional version of these that would live as an open source project though. Going back to the different CPUs, so you can run these types of projects going all the way down to Quark processor, an Edison, which is based on Atom. You can scale it up. In my particular case here, the voice assistant that I was using was being run on a core-based system, which might be overkill, but that core-based system was also responsible for running a database and collecting all sensor data on the network, for running the automation engine, and for running a couple of different services that do logging and spooling of sensor information to the database. It also ran the administrative user interface and an analytics interface. So you can see as you go up in processor power how enabling more services becomes a useful thing. Can you post a link to slides? Where is the info on the commercial IoT lab? Yes, so the info on the commercial IoT lab, if you look for them, there's 2 different places that you can get it. The first one is on Docker. So I've got some of my experiments going here. If you simply type Docker run-d-p, I have a Docker image called ssgdrd IoT/CIOT labs, and we're running on Ubuntu here. If you run this and you have Docker installed, this is going to fetch, I already have it running apparently, but this is going to fetch the labs that are available and let you run it on your local area network. The other thing you can do, and I highly recommend you do, is go to Commercial IoT Labs. Labs, and on software.intel.com. And the labs are posted here as well. So they take you through building out sensors, publishing data, collecting that data, setting up your TLS on your local area network, setting up security, databases at the edge, building your custom interface, administrative interface, building your automation engine, doing remote management with the Helix Device Cloud, and then data analytics. My Twitter handle. Always love to give that out. Twitter handle is right here, Agnathan.